Okay, hello, calculus students. Doing this a little differently this time. I hope this is all right. Section 3.9, differentials and linear approximation. There's just two things we need to worry about here. Differentials, that's just prep work for when we get to next chapter. That's going to be really, really easy. We'll get to that in a second. Most important though for this chapter, linear approximation. So here's what linear approximation is. Estimate the square root of 15.9 using linear approximation, also known as using the tangent line. They might write it that way. How do we do this? This isn't actually too bad. First thing you're going to do is write the equation of a tangent line. So you may say, how do you do that, Mr. Kuhne? I don't know what my function is. Well, the function here is just the square root of x. We're trying to estimate the square root of 15.9. We do this because before the days of calculators, it was hard to get square root of 15.9 just on its own. Calculators made a whole lot of things easier, but getting that answer without this, without linear approximations, is really hard. So this is a good way to get a very, very good, close approximation without actually figuring out the actual answer. We'll talk about why in just a moment. So how do we do this? Step one is write the equation of a tangent line. Okay, so I'm going to use this right here. To do that, of course, we need to find f prime of x. So if f of x is the square root of x, then f prime of x, now remember this is x to the 1/2, f prime of x can be 1/2 x to the negative 1/2, which is 1/2 times the square root of x. That's something that is just good to memorize. You don't have to, but it's good to memorize because that just comes up a lot. Okay, so the derivative of square root of x is 1/2 times the square root of x. Equation of a tangent line. So what we're going to do is we're going to do y minus y1 equals m times x minus x1. We're going to use a point really close to 15.9. Obviously, that's going to be 16, right? So what we're actually, so we're going to take f of 16. So the square root of 16, we know, both know is, we all know is 4. I'm going to plug in my x and y. So there's my x, there's my y. I'm going to plug in 4 right here, 16 right here. Y minus y1, m times x minus x1. My slope. I'm using 16, again, because it's really, really close to 15.9. Super close. So f prime of 16 would be 1/2 times the square root of 16. Right, it's going to be 4, so that's going to be 1/8, right? So 1/8. What we have here is the tangent line. What we have here is the tangent line. It would look, not to scale, but it would look like this. At 16, right here, I've got this tangent line. Correct? Right here, that's where it actually touches. Again, this is not to scale. If I want to know square root of 15.9, I would be looking on this curve down here, the white curve. But what we can do is, because these are so close, again, not to scale, I'm going to say 15.9 is right here. I'm looking for this number technically, but because the tangent line is so close right there, I'm going to use the tangent line to give me the number. I don't know what the square root of 15.9 is, but what I can do is I can come over here and plug in 15.9 into this line. Now I just got to find the y coordinate. All right, so this is going to be negative 0.1. That's going to be 1/8. Now, negative 0.1, I'm just doing the math in my head here. That's the same thing as 1/8 times negative 1/10. That's going to be negative 1/80th. So I'm going to add 4 to both sides. Y is equal to 4 plus negative 1/80th. Okay? When I do this, I plug in, I can figure this out by hand if I need to, but it would just be 3.9875. Here's what we're going to do now. Let's check this. Have out your lightsaber. So they would, this is how they would find approximations before days of calculators, but what I'm going to do is I'm going to type in 15.9, and I'm going to take the square root of that. Square root of 15.9. $3.9874804,074. That's really close to that answer right there, isn't it? In fact, let's subtract them, find out how close we are. Minus sorry about that. That's negative 1.959 times 10 to the negative 5th. That's really, really close. So what we see here is this number right here is really, really close to this number right here because it's on the tangent line. The farther away we get, though, like if I want to do it over here, here's the line. That's going to be a lot farther away. But because these are so close right there, there's a teeny, 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 tiny bit. Just right there. Look, hardly any difference between them. That's a good, what we call linear approximation of this value. So the steps for this, step 1, write the equation of a tangent line. Use a point close to, we'll call it C, whatever that number is. Then finally, plug C into the line to get the approximation. Sorry, that's not very big. Write the equation of a tangent line, use a point close to C, plug C into the line to get the approximation. Those are the 3 steps you do. Write equation of a tangent line, that's nothing new. Okay, so you got to think a little bit to use a point close to C. Then you just got to plug in C. So this isn't anything super new, but the concept behind it's really rather ingenious. I can't figure out this one easily, so I'm going to make a tangent line and use that one to get something like that. I know we would say, hey, it's something close to 4, it's something a little bit less, so it's like 3.99 something. Man, we can get a lot closer with this. So that is linear approximations. There will be a test question like this. There's normally one question, maybe 2 on the AP exam like this. All right, differentials. I'm going to erase this. Differentials. There won't be a question on this test like this, but it sets you up for the next unit. There's a lot of applications of differentials. We're not going to go into them. They're super cool. We're just not going to do it because we only have so much time. And I want to focus on things like the Rocket Lab and, explaining things like that. But there's a good project you can do for differentials if you're interested. Okay, differentials. dx is the differential of x, dy is the differential of y. We know dy over dx is essentially, that's another way of saying f prime of x, correct? This is where you just nod your head. I can't see you, but you nod your head for me. One of the things you can do in calculus, these can actually be separated. I can't separate this, that's an operation. That's like a plus sign or square root sign. I can't separate that. However, I can separate this. This is the change in y over the change in x. The change in y, I can multiply both sides times dx and get dy is equal to f prime of x dx. Congratulations, you just found a differential. Somebody's saying there's got to be more to it than that. No, there's not. There really isn't. So, an example. Find the differential of y. Y is equal to x cubed. What's the differential of y? Well, let's take the derivative of this. dy over dx is equal to 3x squared, correct? How do you get the differential? dy is equal to 3x squared times dx. That's it, you're done. Seriously. Yeah, I told you it was easy. You just multiply both sides by dx. Those cancel out. And you have dy is equal to 3x squared dx. Super easy. Because some of you are still thinking it can't be that easy, let's do one more. Y is equal to sine of x. Okay. What is the differential? Well, first we're just going to take the derivative. Dy over dx is equal to, the sine is cosine of x. To get differential, just dy is the differential of y. So I'm going to multiply both sides by dx to get rid of this down here. dy is equal to cosine of x dx. That's the differential of y. No, it's not hard. There's never going to be a question just asking for differentials, but the fact that you can separate these sets up what happens in the next unit. There's something called U substitution. So there you go. Differentials, linear approximations. Again, first step, write the equation of the line, of a tangent line. Use a point close to the C value, whatever is in there, something that you can easily know. Plug C into the line to get the approximation. And to get the equation of a tangent line, of course, you have to derive whatever function this was. So the function on the outside here was just square root of x. All right, there you go. That's it. Thanks for watching. Yay, math.